Hi students, today I explain the sum of the SAQs of matrices. In the previous videos, I explained the LAQs and sum of SAQs also. Now I explain another some more SAQs of matrices. Okay. Now fifth question. If 3a is equal to 1, 2, 2, 2, 1 minus 2, minus 2, 2 minus 1, then show that A inverse is equal to A transpose. Okay, here A transpose means interchanging of rows into columns or columns into rows. Okay, the problem is solved by using the definition of matrices. That is, if AB is equal to BA is equal to I, then B is equal to A inverse. Okay, but the problem is also solved by you find the A inverse. A inverse is equal to adjoint A by det A. But here A into A transpose is equal to I, which is the easiest method. Therefore, first we consider 3A. 3A is equal to given matrix and A is equal to 1 by 3 into matrix of 1, 2, 2, 2, 1, minus 2, minus 2, 2, minus 1. Now consider A transpose. A transpose is equal to 1 by 3 into interchanging the rows into columns. Then we get A transpose. Now multiplying A into A transpose. That is equal to 1 by 3 into matrix and 1 by 3 into another matrix. 1 by 3 into 1 by 3, 1 by 9 into. Here we use the matrix multiplication. Multiplication of first row with first column is the first element. That is equal to 1 plus 4 plus 4. And first row with the second column is the second element. That is equal to 2 plus 2 minus 4. And first row with third column is the third element. That is equal to minus 2 plus 4 minus 2. Similarly, remaining multiplication. Then that is equal to 1 by 9 into we get 9, 0, 0, 0, 9, 0, 0, 0, 9, which is equal to identity. Dividing by 9, then we get identity matrix of order 3 by 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. Therefore, by definition of inverse of a matrix, A into B is equal to B into A is equal to I, then B is equal to A inverse. Here, A transpose is equal to I implies A inverse is equal to A transpose. Okay, next one is, show that det of y plus z, x, x, y, z plus x, y, z, z, x plus y is equal to 4x, y, z. Okay. Now the expansion is by using row or column operations. Here we use the row operations. Here the first element of first row is y plus z. Therefore first we change this as 0, but for simplification easy. Therefore for this we change r1 changes to r1 minus of r2 plus r3. Then we get the first row as 0 minus 2z minus 2y, and the remaining two rows are same. Y, z plus x, y, z, z, x plus y. Now, by using the determinant expansion, by using first row, expanding the determinant, we get the value that is equal to 4x, y, z. Or also the problem is solved by directly expansion of this determinant. That is by using first row or first column, we get the answer 4x, y, z. Next one is, find the value of x if det of x minus 2, 2x minus 3, 3x minus 4, and second row is x minus 4, 2x minus 9, 3x minus 16, and third row is x minus 8, 2x minus 27, 3x minus 64 is equal to 0. Okay. By using the determinant expansion, we find this value. That is to find the value of x. Here, for simplification, we use row or column operations. We change the each element in each row is the sum or difference of two elements. Therefore, first we change any two rows or any two columns by single elements by using row operations or column operations. Here first we use the row operations. First consider the given determinant. R2 changes to R2 minus R1 and R3 changes to R3 minus R1. By using R1, we change the second and third rows to a single elements. Then we get x minus 2, 2x minus 3, 3x minus 4. Second row is minus 2, minus 6, minus 12. Third row is minus 6, minus 24, minus 60 is equal to 0. Okay. From R2 we take minus 2 common and R3 we take minus 6 common. Or R2 changes to R2 by minus 2 or R3 changes to R3 by minus 6. Then we get x minus 2, 2x minus 3, 3x minus 4, 1, 3, 6, 1, 4, 10 is equal to 0. Now expanding this determinant by using the determinant expansion, by using first row, we get the value x is equal to 4. Okay. Next one is 8th question. Det of 1a square, 1b b square, 1c c square is equal to a minus b, b minus c, c minus a. Okay. Now we take the LHS, prove that RHS. In this determinant, there are 3 ones in first column. Okay. Now we change any 2 ones as zeros. If the ones are in first column, we use row operations. Here we use R2 changes to R2 minus R1 and R3 changes to R3 minus R1. By using R1, we change the 2 ones as zeros in R2 and R3. Then the determinant is 1a square. Second row is 0, b minus a, b square minus a square. And third row is 0, c minus a, c square minus a square. From the second row, we take b minus a, and from third row, we take c minus a as common. Then det of 1a square, 0, 1 b plus a, 0, 1 c plus a. Now expanding this determinant by using first column, then b minus a, c minus a into c plus a minus b minus a. That is equal to a minus b into b minus c into c minus a. Okay, next one is, if a is equal to 2, 1, 2, 1, 0, 1, 2, 2, 1, find the adjoint and inverse of A. Okay, now we find adjoint of a matrix. Adjoint means transpose of cofactor matrix. For this, first we find cofactor matrix. Cofactor matrix means each element is replaced by its cofactors. Okay, first we find each cofactor for each element. Cofactor is equal to minus 1 whole power I plus j into its minor. I means the number of row and j means the number of column in which the element exists. Okay, here consider first element is 2. Therefore, cofactor of 2 is equal to minus 1 whole power I plus j. Here I is equal to first row and j is the first column. Minus 1 whole power 1 plus 1 into its minor is 0, 1, 2, 1. Minor means deleting the first row and first column. Then we get 4 elements. They are 0, 1, 2, 1. Therefore, det of 0, 1, 2, 1. Okay. AD minus BC, we get 0 minus 2. That is equal to minus 2. Similarly, cofactor of 1. Here 1 is the first row and second column element. That is equal to minus 1 whole power 1 plus 2. I plus j. Here I is equal to 1 first row and j is the second column. Therefore, 1 minus 1 whole power 1 plus 2 into its minor is 1, 1, 2, 1. That is deleting the first row and second column. And then for the remaining 4 elements, we find det AD minus BC. That is equal to minus of 1 minus 2, 1. Next, cofactor of 2. Here 2 is the first row and third column element. That is equal to minus 1 whole power 1 plus 3. I plus j means here I is 1 first row and j is third column for plus 3. And its minor 1, 0, 2, 2. Okay. Expanding this, that is equal to 2 minus 0, 2. Next, cofactor of 1. Here 1 is the second row and first column element. Therefore, that is equal to minus 1 whole power 2 plus 1. Its minor is 1, 2, 2, 1. Minor means deleting its row and column in which the element exists. That is equal to minus of 1 minus 4, 3. Next, cofactor of 0. 0 is the element in second row and second column. That is equal to minus 1 whole power 2 plus 2 into its minor. 2, 2, 2, 1. Which is equal to minus 2. Similarly, we find the cofactors of all elements. Then cofactor matrix is equal to minus 2, 1, 2. That is, each element is replaced by its cofactor. For first element, cofactor is minus 2. Second element, 1. Third element is 2. And for the second row, 3, minus 2, minus 2. 1, 0, minus 1. Now we find adjoint. Adjoint A is equal to transpose of cofactor matrix. Okay. Transpose means interchanging the rows into columns. Then we get minus 2, 3, 1. 1 minus 2, 0, 2 minus 2 minus 1, which is equal to adjoint A. Now A inverse is equal to adjoint A by det A. Here det A is equal to we find det 3 by 3 matrix, we get 1 not equal to 0. Therefore, A inverse is equal to adjoint A by det A, which is the required value. Okay, next one is, if A is equal to 1, 2, 1, 3, 2, 3, 1, 1, 2, then find A inverse. Okay, again A inverse is equal to adjoint A by det A. First we find det A. Det A is equal to det of 1, 2, 1, 3, 2, 3, 1, 1, 2. Okay, by using the first row, expanding this determinant, its value is minus 4, not equal to 0. Therefore, det A is not equal to 0. Okay, now we find adjoint matrix. Adjoint is equal to transpose of cofactor matrix. Cofactor matrix is each element is replaced by its cofactors. Therefore, we find the cofactors for each element. Here the first row element is first column element is 1. Therefore, cofactor of 1 is equal to minus 1 whole power I plus j into its minor. Here I is the number of row and j is the number of column in which element exists. Here that is equal to minus 1 whole power 1 plus 1 into its minor is 2, 3, 1, 2. Expanding this we get 1. Similarly, cofactor of 2. Here 2 is the first row second column element. That is equal to minus 1 whole power 1 plus 2 into its minor. Minor means deleting its row and column in which 2 exist. Then the remaining 4 elements are 3, 3, 1, 2. Okay, by using AD minus BC, we get minus 3. Similarly, cofactor of 1. Here 1 is the first and third column element. That is equal to minus 1 whole power 1 plus 3 into its minor is det of 3, 2, 1, 1. That is equal to 1. Similarly, we find the cofactors of each element. Then, cofactor matrix is 1, minus 3, 1, minus 3, 1, 1, 4, 0, minus 4. Adjoint A is equal to cofactor of transpose. Transpose of cofactor matrix. That is equal to adjoint A is equal to transpose means interchanging the rows into columns or columns into rows. We get 1, minus 3, 4, minus 3, 1, 0, 1, 1, minus 4. Okay. Therefore, A inverse is equal to adjoint A by det A. That is equal to 1 by minus 4 into 1, minus 3, 4, minus 3, 1, 0, 1, 1, minus 4. Next one is, if I is equal to 1, 0, 0, 1 and E is equal to 0, 1, 0, 0, then show that AI plus BE whole cube is equal to A cube I plus 3A square BE. Now, consider the given two matrices I and E. AI plus BE is equal to A into I 1, 0, 0, 1 plus B into 0, 1, 0, 0. Here A comma B are real numbers, some scalars. Here we use scalar multiplication of a matrix. Scalar multiplication means each element in a matrix is multiplied by scalar. Here A comma B are scalars, therefore multiplied by A with each element of the first matrix. That is equal to A0, 0A plus B into 0, 1, 0, 0 is equal plus 0, B, 0, 0. That is each element. Scalar multiplication of a matrix is each element is multiplied by a scalar. Okay. Adding these two, matrix addition is corresponding elements are add. That is equal to A plus 0. Corresponding elements means first row first element, second determinant, second matrix first element. Here the first matrix first element is A. In second matrix first element is 0. Therefore A plus 0, A. Next 0 plus B, B. 0 plus 0, 0. A plus 0, A. Now AI plus BE whole square. That is equal to A plus BE into A plus BE. Multiplying these two matrices. Here we use the multiplication of matrices. That is multiplied the first row with the first column of an element. First column of a second matrix. That is equal to A square plus 0. AB plus AB and 0 plus 0. 0 plus A square. That is equal to A square 2AB 0 A square. And A plus B whole cube is equal to A plus B whole square into A plus B. Again, multiplying these two matrices, multiplication of a matrices, we get A cube plus 3A square B 0 A cube. Now we consider the RHS. RHS is A cube I plus 3A square BE. That is equal to A cube into 1001 plus 3A square B into 0100. Okay. First matrix is multiplied by a cube means each element is multiplied by a cube. A cube 0 0 a cube plus second matrix each element is multiplied by 3a square b. 0 3a square b 0 0. Adding these two we get a square a cube 3a square b 0 a cube. Okay, from 1 and 2 we get the required value. If a is equal to 7 minus 2 minus 1 2 5 3 and b is equal to minus 2 minus 1 4 2 minus 1 0, then find a b dash and b a dash. Here a dash comma b dash are transpose of matrices of a and b respectively. Transpose means replace, interchanging the rows into columns or columns into rows. Okay, now consider a and b given two matrices. Now a transpose is equal to, here in first row is 7 comma minus 2. In a transpose 7 comma minus 2 is the first column. Therefore a transpose is equal to 7 minus 2 minus 1 2 5 3. And b transpose is equal to minus 2 minus 1 4 2 minus 1 0. Now a b dash which is equal to a b transpose, multiplication of a with b transpose. 7 minus 2 minus 1 2 5 3 is of order 3 by 2, and b transpose is minus 2 4 minus 1 minus 1 2 0 is of order 2 by 3. Here the matrix multiplication exists. Then multiply these two matrices by using multiplication of matrices. That is, multiply the first row of the first matrix with the first row of the second matrix. That is equal to 7 into minus 2 minus 14 plus minus 2 into minus 1 plus 2 is the first element. Next, multiply the first row with the second column of the second matrix. 7 into 4 28 minus 2 into 2 minus 4, which is the second element, and multiply the first row with the third column of the second matrix. 7 into minus 1 minus 7 minus 2 into 0 plus 0 is the third element in first row. Similarly, multiply the second row with the first column is the first element, and second column is the second element, and third column is the third element. Next, multiply the third row with first column, second column, and third column. We get the matrix minus 12, 24, minus 7, 0, 0, 1, minus 13, 26, minus 5. Similarly, we find B A dash. A dash means A transpose. Okay, here B is equal to B A dash or A transpose is equal to B is equal to minus 2, minus 1, 4, 2, minus 1, 0, and A dash means transpose of the matrix A. That is, 7 minus 2 is the first row in A, then its transpose 7 minus 2 is the first column. 7 minus 2 minus 1 2 5 3. Again, multiplication of these two matrices exist, and which is the required value. Okay, next one. If A is equal to 3 minus 3 4, 2 minus 3 4, 0 minus 1 1, then show that A inverse is equal to A cube. Okay. First we find A square and A4. A square is equal to A into A. That is multiplication of these two matrices. By using multiplication of matrices, that is multiplied the first row with the first column is the first element. That is 9 minus 6 plus 0. And first row with the second column is the second element. Minus 9 plus 9 minus 4. And first row with the third column is the third element. 12 minus 12 plus 4. And so on multiplying, we get 3 minus 4 4, 0 minus 1 0, minus 2 2, minus 3. Then A power 4 is equal to A square into A. Multiplying again these two matrices, we get identity matrix 1 0 1, 1 0 0, 0 1 0, 0 0 1. That is, A power 4 is equal to I. Multiplying both sides with A inverse, then A inverse into A power 4 is equal to I into A inverse. Okay. A inverse into A power 4 is equal to A inverse into A cube, which is equal to I into A inverse is A inverse. Then A cube is equal to A inverse, and det is also not equal to 0. Therefore, inverse of a matrix exists, and A cube is equal to A inverse. Show that det of BC, B plus C 1, CA C plus A 1, AB A plus B 1 is equal to A minus B, B minus C, C minus A. Okay, we consider LHS and then we prove that RHS. First we consider the given date. BC B plus C 1, CA C plus A 1, AB A plus B 1. We observe that in the last column there are 3 ones. Okay, if each element or each element in a row or a column contains 3 ones, then we change any 2 ones as zeros. Here the ones are in column, therefore by using row operations we take any 2 ones as zeros. For this we use R1 to change ones as zeros in R2 and R3. By using row operations, R2 changes to R2 minus R1 and R3 changes to R3 minus R1. Here we use R1, therefore R1 is unchanged. BC B plus C 1 and second row is CA minus BC, C plus A minus B minus C 1 minus 1. Third row is AB minus BC, A plus B minus B minus C 1 minus 1. Simplifying we get BC B plus C 1 is the first row and second row is C into A minus B 0 and third row is B into A minus C 0. Now from the second row we take A minus B common and from third row we take A minus C common. Then we get A minus C or C minus A we take common, then det of BC B plus C 1, C 1 0 and minus B minus 1 0. Here we take C minus A common, therefore third row is minus B minus 1 0. Now expanding this treatment by using last column, that is equal to A minus B C minus A into minus C plus B. We get A minus B, B minus C, C minus A. Okay, next one. If A is equal to 1, 4, 7, 2, 5, 8, B is equal to minus 3, 4, 0, 4, minus 2, minus 1, then prove that A plus B whole transpose is equal to A transpose plus B transpose. Now consider the given two matrices. First we find A plus B, addition of these two matrices. Here A and B have the same order, therefore addition of these two matrices exist, and addition of the matrices can be defined as corresponding elements are add. That is, in first row, in first matrix, first element is 1, add with the first element in second matrix, that is equal to 1 minus 3 is the first element, and we add first row second element of the first matrix with first row second element of the second matrix, that is 4 plus 4 8. Similarly adding these two matrices, that is addition of two matrices means add the corresponding elements, then we get minus 2 8 7 6 3 7. Now A plus B whole transpose. Transpose means interchanging the rows into columns, that is equal to minus 2 8 7 6 3 7. Take this as equation 1. Now RHS is A transpose plus B transpose. We consider A transpose plus B transpose, which is equal to A transpose is 1 4 7 2 5 8 plus B transpose is minus 3 4 0 4 minus 2 minus. Similarly adding these two matrices by using the definition of addition of matrices, we get minus 2 6 8 3 7 7. Take this as equation 2. Now from 1 and 2, these two are equal, therefore A plus B whole transpose is equal to A transpose plus B transpose. Okay, next one. If A is equal to 2 minus 4 minus 5 3, find A plus A dash and A dash. Here A dash is transpose of A. Now consider A plus A transpose or A plus A dash, that is equal to 2 minus 4 minus 5 3 plus 2 minus 5 minus 4 3. Here A dash is transpose. Transpose means interchanging the rows into columns or columns into rows. Now by using definition of addition of matrices, we get 4 minus 9 6. That is, we add the corresponding elements. 2 plus 2 minus 4 minus 5 minus 5 minus 4 3 plus 3. Okay, now A dash, that is the product of the matrices. First A is 2 minus 4 minus 5 3 and A dash is 2 minus 5 minus 4 3. Multiplying the first row with first column, 2 into 2, 4 plus 16 is the first element. Next, first row with the second column, minus 10, minus 12 is the second element. Multiply the second row with the first column, minus 10, minus 12. Next, 25 plus 9. We get 20, 22, 20, minus 22, 34. Next one, if A and B are invertible, then show that AB is also invertible and AB whole inverse is equal to B inverse A inverse. Now consider A is invertible matrix implies A inverse exists, and by definition of inverse of a matrix, A inverse is equal to A inverse into A is equal to I. Similarly, B is invertible matrix, therefore B inverse exists, and B inverse is equal to B inverse B is equal to I. Now we prove that AB whole inverse is equal to B inverse A inverse. For this, first we consider AB into B inverse A inverse. Okay, that is equal to A into B inverse into A inverse. Here B inverse is equal to I. Therefore A inverse, which is equal to A into A inverse, that is equal to I. Similarly, consider B inverse A inverse into AB. Again, rearranging the terms, matrices, we get B inverse B is equal to I. Therefore, by definition of inverse of a square matrix, if AB is equal to BA is equal to I, then B is equal to A inverse. Therefore, here AB into B inverse A inverse is equal to B inverse A inverse into AB, that is equal to I. Therefore, AB is invertible and AB whole inverse is equal to B inverse into A. Next one, if A is equal to 1, 2, 2, 2, 1, 2, 2, 2, 1, then show that A square minus 4A minus 5I is equal to 0. Now consider the given matrix. A square is equal to A into A. That is equal to product of the two matrices 1, 2, 2, 2, 1, 2, 2, 2, 1 into, again we consider A 1, 2, 2, 2, 1, 2, 2, 2, 1. Multiplying these two matrices means multiplication of first row with first column of the second matrix, which is the first element, that is 1 plus 4 plus 4. Multiply the first row with the second column is the second element. Multiply with first row with third column is the third element. Similarly, multiplication of second row with first column, second column, third column, and multiplication of third row with first column, second column, third column, that is equal to, you get 9, 8, 8, 8, 9, 8, 8, 8, 9. Now consider the LHS A square minus 4A minus 5I, that is equal to, substitute all these values and adding all the matrices, we get 0, 0, 0, 0, 0, 0, 0, 0, 0. Here we use the addition of matrices. Addition means adding the corresponding elements of the matrices. Any n by n matrix, A, prove that A can be uniquely expressed as a sum of a symmetric matrix and skew symmetric matrix. Okay, now consider A be a square matrix. A can be represented as A is equal to A plus A transpose plus A minus A transpose by 2. That is equal to A plus A transpose by 2 plus A minus A transpose by 2. Now, let A is equal to B plus C. Here B is equal to 1 by 2 into A plus A transpose and C is equal to A minus A transpose. Here, if A is a symmetric matrix means A transpose is equal to A, and skew symmetric matrix, then A transpose is equal to minus A. Now we prove that A can be uniquely expressed as the sum of symmetric and skew symmetric matrices. Here now we prove that B and C are, one is symmetric and C is skew symmetric matrix. If B is a symmetric matrix, then B transpose is equal to B. For this, first we consider B transpose, that is equal to A plus A transpose by 2 whole transpose, which is equal to 1 by 2 into A transpose plus A. Here we use A transpose whole transpose is equal to A, therefore which is equal to B. Therefore B is symmetric matrix. Now we prove that C is a skew symmetric matrix. For skew symmetric matrix, C transpose is equal to minus C. Therefore first we consider C transpose, 1 by 2 into A minus A transpose whole transpose, that is equal to 1 by 2 into A transpose minus A. Okay. Again here use A transpose whole transpose is equal to A. Therefore, we take minus common, minus 1 by 2 into A minus A transpose minus C. Therefore, C is a skew symmetric matrix. Therefore, A is equal to B plus C. Here B is symmetric and C is skew symmetric. Therefore, every square matrix can be expressed as a symmetric and skew symmetric matrices. Okay, now A can be uniquely expressed as a sum of symmetric and skew symmetric matrices. For this, first we verify uniqueness. Uniqueness means there exists only one and only one matrix. Suppose, if possible, A is equal to P plus Q, where P is symmetric and Q is skew symmetric matrix, then A transpose is equal to P plus Q whole transpose. That is equal to P transpose plus Q transpose, which is equal to P minus Q. Here, P transpose is equal to P and Q transpose is equal to minus Q. Now, A plus A transpose is equal to 2P, implies P is equal to 1 by 2 into A plus A transpose, which is equal to B. Similarly, A minus A transpose is equal to 2Q, implies Q is equal to 1 by 2 into A minus A transpose, C. Therefore, A is equal to P plus Q, which is also B plus C, P plus Q, which is also equal to B plus C. Therefore, A can be uniquely expressed as a sum of symmetric matrix and skew symmetric matrix. Show that the determinant of a skew symmetric matrix of order 3 is always 0. Okay, skew symmetric matrix means A transpose is equal to minus A. Okay, now consider A is a skew symmetric matrix of order 3. Now we consider det of A transpose, that is equal to det of minus A. Since A transpose is equal to minus A, we take det on both sides, implies det A transpose is equal to det minus A. Here, det A transpose is equal to det A. Okay, implies det A is equal to minus 1 whole cube into det A. Here we use the condition det Ka is equal to, here K is some scalar, K power n into det A, where n is the order of the matrix. Therefore, here A is a 3 by 3 matrix. Therefore, minus 1 whole cube into det A. Therefore, det A is equal to minus det A. Implies rearranging terms, we get 2 det A is equal to 0. Det A is equal to 0. Therefore, the determinant of a skew symmetric matrix of order 3 is always 0. Or, there is another method. Take some example. Here, for skew symmetric matrices, principal diagonal elements are always zeros. Therefore, consider A is equal to 0 minus C minus P, C 0 minus A, B A 0. Here A is a skew symmetric matrix. Now consider det. By expanding the determinant by using first row, we get the value 0. Okay, next one. If A is equal to 1 minus 2, 1, 0, 1 minus 1, 3 minus 1, 1, then find A cube minus 3A square minus A minus 3I, where I is unit matrix of order 3. Okay. Now consider the given matrix A. We find A square. A square is equal to A into A. In this problem, we use the multiplication of matrices and addition of the matrices. First, for A square, A into A, here we use the multiplication of matrices. Okay, consider that is equal to 1 minus 2, 1, 0, 1 minus 1, 3 minus 1, 3, 1 into, again we consider det matrix A, 1 minus 2, 1, 0, 1 minus 1, 3 minus 1, 1. Okay, multiplication of matrix means multiply the first row of the first matrix with first column of the second matrix is the first element. That is equal to 1 minus 0 plus 3. Next, multiplying first row with the second column is the second element. Next, multiply the first row with the third column is the third element. Similarly, multiplied with the second row with first column, second column, third column are the three elements in second row. And multiply the third row with first column, second column, third column are the three elements in third row. Simplifying, we get 4 minus 5, 4, minus 3, 2, minus 2, 6, minus 8, 5. Again consider A cube, which is equal to A square into A. Same as above, multiplying, we get the A cubes. 16 minus 17, 13, minus 9, 10, minus 7, 21, minus 25, 19. Similarly, A cube minus 3A square minus A minus 3I, that is equal to A cube minus 3 into, substitute all these values. Here A cube is equal to 16 minus 17, 13, minus 9, 10, minus 7, 21 minus 25, 19, minus 3 into a square is 4 minus 5 4 minus 3 2 minus 2 6 minus 8 5 minus here a is 1 minus 2 1 0 1 minus 1 3 minus 1 1 minus 3 into I is identity matrix of order 3 by 3 1 0 0 0 1 0 0 0 1. Okay, simplifying we get the value of 0, that is equal to null matrix. Okay, next one, if a is equal to minus 1 minus 2 minus 2 2 1 minus 2 2 minus 2 1, then show that the adjoint of a is 3a transpose and find a inverse. Okay, first we find the adjoint matrix. Adjoint means transpose of cofactor matrix. Okay, for this first we find cofactor matrix. Cofactor matrix means each element of a matrix is replaced by its cofactor. In the previous problems we solved the cofactors of different elements in a matrix. Therefore, by using this method, cofactor A is equal to, that is cofactor matrix of A is equal to minus 3 minus 6 minus 6 6 3 minus 6 6 minus 6 3. Now adjoint A is equal to transpose of cofactor matrix. Transpose means interchanging the rows into columns or columns into rows. Then we get minus 3 6 6 minus 6 3 minus 6 minus 6 minus 6 3. Take this as equation 1. Now consider A transpose. A transpose is equal to, changing the rows into columns, we get minus 1 2 2 minus 2 1 minus 2 minus 2 minus 2 1 is the third row. Now 3A transpose is equal to 3 into A transpose. Okay, here we use a scalar multiplication. Scalar multiplication means each element is multiplied by a scalar. Here 3 is a scalar, therefore multiplied matrix A transpose with each element with 3. That is equal to minus 3 6 6 is the first row. And second row is minus 6 3 minus 6. Third row is minus 6 minus 6 3. Okay. Here adjoint A is equal to 3 into A transpose. Therefore first one is proved. Next we find A inverse. A inverse is equal to adjoint A by det A. Okay, first we find det A by using definition of determinant. Det A is equal to 27. Therefore A inverse is equal to 1 by 27 into adjoint A, which is equal to 1 by 9 into minus 1 2 2 minus 2 1 minus 2 minus 2 minus 2 1.